In this video, we will study simultaneous linear equations. We know that we require as many number of equations as there are variables in the equations, which means that if there are n number of variables, we require n number of equations to solve them. For a linear equation in one variable, a single equation is sufficient to find the value of the variable. For equation in two variables, we require two linear equations to find the value of the two variables. For equations in three variables, we require three linear equations, so on and so forth. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. In a system of linear equations in one variable, ax equals b, where a and b are real numbers and x is the unknown, there are three possibilities. Number one, if a is not equal to 0, then the equation has a unique solution, which is x equals b upon a. Number two, if a and b both are 0, then the equations will have infinity of solutions. Number 3, if a equals 0 but b not equal to 0, then the equation reduces to 0x equals b, that is 0 equals b, which contradicts the assumption b not equal to 0. Therefore, this is absurd and we say that the equation is inconsistent without any solution. According to the first possibility, we can show the solution geometrically as origin x equals b upon a on the x-axis. We can show the second possibility with infinity of solutions like this. And since the third possibility has no solution, there is no need to show geometrically. So this figure shows unique solution while this figure shows infinity of solution. In system of equations in two variables, say for example equations 2x plus 3y equals 5 and 4x plus 3y equals 7. In order to solve this equation, we will subtract second equation from the first one to get minus 2x equals minus 2. Hence x equals 1. To get the value of y, we will substitute x equals 1 in the first equation to get 3y equals 3 and hence y equals 1. So the unique solution of these two equations will be 1, 1, which we can show geometrically by two intersecting lines which intersect in this unique point 1, 1. Consider this pair of linear equations in two variables. 2x plus 3y equals 5 and 4x plus 6y equals 10. If we take 2 common from the second equation, then we get 2 times 2x plus 3y equals 2 into 5. Cancelling 2 from both sides, we get the same equation as in 1, 2x plus 3y equals 5. So therefore, we find that these two equations are one and the same. Their geometrical representation will be two coincident lines, both having the same equations given here. So these being coincident lines, there will be infinitely many solutions of these two equations. Let's consider these two equations in two variables. 2x plus 3y equals 4 and 2x plus 3y equals 6. First equation can be written as y equals minus 2 upon 3x plus 2, and the second equation can be written as y equals minus 2 upon 3x plus 3. Now since these two equations have same slope minus 2 upon 3, these two lines will be parallel to each other and can be geometrically represented like this. Now since these two parallel lines don't intersect each other, there will be no solution of these two equations. Now we will talk about system of equations in three variables. Consider these three equations: 2x plus 3y plus 5z equals 10, 3x plus 6y plus 2z equals 11, and x plus y plus 4z equals 6. If we compare these three equations with general equation of plane ax plus by plus cz plus d equals 0, we understand that each of these equations is equation of a plane. We can find that these equations are consistent and hence they have unique solution 1 comma 1 comma 1, which means these three planes intersect in this point 1 comma 1 comma 1. Geometrically we can show this like this. So this is the point 1 comma 1 comma 1 where these three planes intersect. Therefore we say that this system of equations in three variables have unique solution. Consider these three equations: 2x plus 35y minus 39z plus 12 equals 0, 6x plus 6y minus 7z minus 8 equals 0, and 12x minus 15y plus 16z minus 28 equals 0. We can find that these three equations have infinite number of solutions, and geometrically this means these three planes intersect in a line. Consider these three equations: x plus 2y plus 3z plus 4 equals 0, 3x plus 6y plus 9z plus 12 equals 0, and 2x plus 3y plus 4z plus 5 equals 0. Here if we take 3 common from this equation, then it becomes x plus 2y plus 3z plus 4 equals 0. Dividing throughout by 3, we get x plus 2y plus 3z plus 4 equals 0, which is same as this first equation, which means that the first equation and the second equation, they are one and the same. We can find that these three equations have infinite number of solutions, which geometrically means first two planes are coincidental, which intersect this third plane in a line like this. Consider these three linear equations: 2x plus 3y plus 4z equals 7, 4x plus 6y plus 8z equals 14, and 6x plus 9y plus 12z equals 21. If we take 2 common from this second equation, then it becomes 2 times 2x plus 3y plus 4z equals 2 into 7. Cancelling this 2 from both sides, we get 2x plus 3y plus 4z equals 7, which is same as the first equation. Also, we can take 3 common from this equation 3 and write 3 times 2x plus 3y plus 4z equals 3 multiplied by 7. Cancelling 3 from both sides, we get 2x plus 3y plus 4z equals 7, same as the first equation, which means that this system of three equations contains one and the same equations. So geometrically it means these three equations represent three coincidental planes, and the system of equation has doubly infinite solution. Consider a system of equations in three variables: x plus 2y plus 3z equals 5, 2x plus 4y plus 6z equals 11, and 3x plus 6y plus 9z equals 13. Here this second equation can be written as dividing throughout by 2, x plus 2y plus 3z equals 11 upon 2. Third equation can be written as dividing throughout by 3, x plus 2y plus 3z equals 13 upon 2. We observe that the left hand side of equation 1, equation 2 and equation 3 is the same, but the right hand side is different, which means that these system of equations in three variables represent three parallel planes like these, and since these planes do not intersect, therefore this system has no solution. Consider system of equations in three variables: 2x plus 3y plus 4z equals 5, 2x plus 3y plus 4z equals 8, and 4x plus 5y plus 3z equals 11. In these equations, we observe that in the first and second equations, the left hand side is same but the right hand side is different, which means that these two planes are parallel planes, while the third plane intersects these parallel planes, and geometrically we can show this like these two parallel planes and third plane intersecting these two planes in these two lines. Obviously, this system of equations will have no common solution. Finally, consider following system of equations: 2x plus 3y plus 4z equals 5, 4x plus 6y plus 8z equals 10, and 2x plus 3y plus 4z equals 7. If we take 2 common from the second equation, then it will be 2 times 2x plus 3y plus 4z equals 2 multiplied by 5. Cancelling 2 from both sides, we get 2x plus 3y plus 4z equals 5, which is the same equation as equation 1, which means that first two equations represent one and the same plane or two coincidental planes like these, and in the third plane, though the left hand side is same as the left hand side of the first equation, but the constant term is different, so therefore this third equation represents a plane which is parallel to these first two planes. So, two coincidental planes are parallel to this third plane. Obviously, there will be no common solution of this system of equations in three variables. Friends, if you like this video, please click the like button, share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.